So here we are in working again in SolidWorks, and in this video I'm going to show you how to make some tweaks to your mechanical model that will perhaps improve the performance of the part directly. And we can use the numerical simulation, the finite element analysis result, to actually feed back to the design and see what maybe we should consider changing in the design. Here we are back in the CAD model that I produced in a previous video. I want to go back to the model, which is easy to do in SolidWorks. As you've seen, it's a bit more complicated to do in ANSYS. So the trade-off is this is convenient, but gives you minimal control on the finite element analysis, whereas ANSYS gives you so much more control of the FEA modeling procedure, and yet the part design modeling is a little bit more time-consuming and difficult. But I can go to this part. I'm just going to save the current part, and then I'm going to save as a new part. Now, in the sketch, I want to put some radii here. I'm even just going to put a 2 millimeter radius. If I put that there, that's a bit too big. I'm going to put a 2 millimeter radius there, and there, 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 there. And because 2 millimeter was too much, I'm going to just do a 0.5 millimeter radius there. So that's all I've changed to the part, nothing else. Just put those sharp corners, made them a bit less sharp. If I go to my static analysis, I need to remesh. Now you can see, looking at the mesh, that over here, my mesh element size is actually on the same scale or maybe even smaller than the detailed feature that I want to reproduce, which is really important. And similarly over here. So those sharp corners have now gone. I haven't changed the sharp corner here that we knew was a high stress area. But let's see what we get. Now looking at the stresses again, I've still set this up so that what we're seeing is my yield stresses at the maximum. And now everything that is red, it has yielded. And notice that, first of all, this zone up here that we'd seen in the previous run is a little smaller than it was before, which means that we've yielded less of the material. We've distorted less of the material. In this region here, we've actually, looks like we've yielded more of it, but in fact what's happened is we've really matched the result with a better model of our mesh. So we're actually resolving more correctly here what the stress might actually be. And we can look at changing, changing this to, let's maybe make that a bit bigger. So we can see a bit more of the extremely high yielded. So you can see that with that, yes, we definitely are looking at high stress in these corners still. The corners over here, though, where we gave the 2 millimeter, that's a lot more more gentle. So by changing to this 2 millimeter radius, we took away some of that yield that we'd seen before. Now you can see that we didn't change anything here, and we're still seeing this artifact from the support conditions. So let's go back and change our model yet again. Now we can take that sketch and we can say, well, a 0.5 millimeter there was perhaps not enough. And if we can run this study again, I haven't changed anything with the mesh, it's meshing now. And those artifacts of yielding are still there. So we're not going to get rid of the high stress areas there quite so easily. But if we look at the actual stresses of those points, we will see that, that they're a bit lower. And we can use a probe, and we can probe a specific point, say here. And so we can look at the stress at that point, and that's 4.64, which is twice what the yield stress is. So that's still an area of concern. We can also probe the stresses at this point, and we're definitely yielding on that edge. And so we can look and see what could we do to improve that. And this is where going back and revising the shape of the designed part will make a big difference. That's a quick look at ways to modify the mesh and use the simulation to drive some basic design principles in your part design. That when we're looking at the combination of meshing to get the resolution of the high stress areas as compared with the actual part itself, then we really want to look at what's reasonable in terms of the mesh size and what's reasonable in terms of the actual part. Now, making a part that has a sharp inside corner is going to be like making a part that has a knife edge in the middle of it that will be cutting through the material. So using this stress analysis to identify those spots and then try to tweak the details of your design is a good and simple approach that you can work with. Let's look at comparing a part that we designed that had very sharp internal corners and high stress areas with adding a little bit more refinement to that design. And we can look at the ultimate deflection of it from the from the simulation to see what the result is. And in this case, the total displacement is 2.8 millimeters. So that would be the displacement out here at wherever the maximum point is. And we can see from the red that the maximum displacement is right here on this point, 2.8 millimeters, which is quite a lot. We've gone from 2.8 millimeters to 2.7 millimeters. All we did was change those radii that weren't even a big deal to change, and we've reduced the total displacement by quite a few percentage points. So we've reduced the motion of this. We've made the entire structure that we've created more stiff. So we've made it a better part just by changing those radii. Now I didn't change the one at the very tip. So I've made no other change. I've added a little bit of material to this part, not a huge amount. And let's see if that's had any significant effect on the load, on the deflection and the model. So now, just like previously, we've gone from, we started out at 2.8 millimeter deflection here at the point on the tip. And by adding curves at the corners of these internal cutouts and a curve at this corner, we've reduced the total deflection from 2.8 millimeters to 2.6 millimeters, which is a significant change given how minimal our design revision was. Let's try one more. So now I cut this part in such a way that we have sharp corners in here. I'm going to add some fillets. I'm going to add just nothing more than a 2 millimeter fillet, which is going to be quite big, really, here and here. So now I've made these corners a little bit more gentle. Let's see if that has an effect on our model. And now you can see that it solved it. The stresses that I've created are a little smoother. The deflection is a little smaller, 2.6, than it was in the previous. And you'll see that the stress concentrations in the corners here will be a little bit more gentle. Now, I've done nothing to improve this corner, and maybe that's the next thing. So I've taken away the sharp corner at the bottom here. And now, by changing that high stress area, I went from originally, the first simple model that I made, I had a 2.8 millimeter deflection. Now I've gotten that down to 2.2 millimeters. That's a significant change in the deflection or the stiffness of this part with very minimal change in the cost to manufacture it. Really, if this was something that was going to be welded or machined, the difference in price to have that part made is basically nil. So those tiny little design changes, and now you can look here and see really there's only a small area that's close to yield here. If I change this color scale back to the yield point, I guess that's what we're at now, then really this part went from being something that was going to be deformed with the load that I'd specified to one that essentially isn't. Now there's some high stressed areas certainly, but we've gotten rid of the really high yielded areas, except for these corners, which as I've said are due to the artifact of the support conditions. And we've made a part that compared to where we started is almost insignificantly different in the cost and the design, and yet in terms of its functionality significantly improved. We've gone from 2.8 millimeter deflection at load to 2.2 millimeters for no cost. So this is what the value you can get from doing finite element modeling as part of your design is all about. It's not about coming up with pretty pictures. It's about using the finite element modeling tool to actually help you improve your design. So let's recap. So we set up some boundary conditions. We made a bracket. We started off with a really simple model of a bracket that had some inherent features that were problems in it. We used the simulation, first of all, to tweak the mesh to make the mesh appropriate for the part we were looking at. And then once we had a mesh that we were sort of comfortable with, now again, you'd be doing a lot more analysis of that mesh and looking in detail at comparative mesh parameters first. But once we were comfortable with the mesh, then making some small design improvements just in the details, we could actually tweak that design to make it better and better.